All right, class. I am going to try this again and see if we can do it a little better this time. Yes, what you don't know about, because you're not going to be put through that, is I tried to do it in higher definition and then put it up on YouTube or whatever. But the higher definition was so bad that I mean, it was such a large file. There was no way that I could put it up there, and I wasn't going to break it into two 15-minute segments. So what I've done is I've gone back to the lower resolution with the less wide angle. I don't even know why I put that on. And I'm gonna write larger or whatever. And I also have multiple different color pens. I'm not sure if they work or not, but if they do, I'll get even different color pens to draw on here, because this is in color, isn't it? It's like real life in color. Now, today, I'm going to be rewriting this all over again. I'm going to show you what I actually had here. This is what I wrote down before and spent a half hour doing it, and then found out the file was way too large. I tried every type of way to get it down, but then it lost so much resolution, it was worse than if I just redid the lecture. So, and I've also learned a couple things, and that's what I want to point out to you as engineers, because what is an engineer? A consummate problem solver, right? So I want to point out to you that as engineers, sometimes you have to take the step back, right? I thought, well, there's got to be a video converter out there, and I tried for a while, and you try, and then you say to yourself, okay, well, look, I'm going to go back to what I know works. And then I'm going to see if I can modify that. And also what I came up with is that I can actually take this now and put it on my copier here, scan it in, and then scan you the notes so that you would have the notes for the class like this. Where do we really fall down on this type of instruction, though? And that point is that right now it's asynchronous. True, you could use Zoom and do it just like a regular class, but then you would lose out on a lot of what can be written on the board. And what I want to do is I want to actually change the instruction a little bit and be able to go more in depth. And I think this way, you watching what I'm writing and everything else to get to the point of this and understanding it, right? That's where you still have to sit in front of this and watch it. So today, what we're going to be talking about is power, right? Today we're going to talk about power, and we're going to talk about it as how it relates. And I'm sure that this lecture, being the second lecture in this, just like for a comedian, you know, you have all your jokes down at all the various different points in there. Joke one. So that just was joke one, if you missed it. So anyway, this should go off a little bit better because I now have my notes for the lecture. So let's start just with a little review. So Z sub R equals R plus J0. And of course, everything that's impedance is in ohms, just like resistance is in ohms, reactance is in ohms. The whole thing, the impedance is in ohms too. So if we look at an inductor, we know that an inductor, theoretically a perfect inductor, has no resistance, but it does have impedance, and impedance is omega L. And again, yesterday when I was talking to you, don't think that impedance is not a way where there is a wasted energy, right? There's still wasted energy, and the way that the energy is wasted in impedance is that it expands the waveform. If you think about it, if energy equals Planck's constant times the frequency, then if the frequency goes down, if the wavelength gets bigger, the frequency gets smaller, right? It's an inverse relationship between frequency and wavelength, as it should be, because they're, you know, the two of them together, frequency times wavelength, equals the velocity of propagation, which through the air is the speed of light, close to the speed of light. But through other media like glass, of course, where we got an index of refraction of 1.5 for glass, the speed is only 2/3 the speed of light. Anyway, that's a different lecture for electromagnetic field theory, which you guys may not get unless you take it as an elective your senior year. So this is the thing, of course, that's ohms. Omega L, I say omega, you say 2 pi radians per cycle times frequency, which is in cycles per second. And the cycles cancel out, giving you radians per second, right? Radians per second. So those are all of our things so far. As far as the three, I should say the capacitance, the first two, but the capacitance also theoretically, and this is much more close to realistic in real life capacitors than it is in real life inductors, it has zero resistance. Plus, now I like to say plus J, and like I said before, I like to put the -1 over omega C in the reactance instead of putting that negative out in front, right? Because as we know, whenever we look at impedance, it's always going to be R plus JX. And that's a plus there. It's not a plus minus. You don't put the minus out here in this. It's 0 plus J and then minus. Really what it refers to is it refers to 180 degrees, right? Because if you think of the complex plane, let me just draw the complex plane down here. And of course, the last lecture we spent talking about the unit circle, but the complex plane is very similar to unit circle, isn't it? Except that the x-axis here is the real numbers and the y-axis is the imaginary, or, you know, J numbers. And of course, they're not really imaginary. They still have a real manifestation. We just use the term imaginary. They're not imaginary. Don't think of them as imaginary. But we've got the real and so anyway, when we're looking at this and looking at what the impedance of something is, if we know that this is R, right, our distance along the x-axis, and then we know that this distance here is x, we can describe this in a complex number notation like we have there, or we could describe this in a magnitude, like a vector representation, right? So we've got a magnitude and an angle of rotation off the real axis. So how would I really write that? Well, of course, if I wanted to just write Z in a general way as a magnitude, that would just be the square root of x squared, which is the reactance, plus r squared, which is the resistance here. And of course, I've got a right triangle. So, and take the square root of that, just like Pythagoras' theorem, and that would give us the impedance that we have right here, Z. Now, to get the angle, the angle would just be the inverse tangent. Why do I say inverse tangent? Because if I've got the angle here, the tangent of that angle is x over r, right? Everybody knows that. The tangent of an angle in a right triangle is the opposite side over the adjacent side. And so that's what I've got. So I'm going to use that information to find out what the angle is. That's just the inverse tangent now, which is the inverse function on your tangent key. And that gives me what the z would be. Now, we can easily do that for the 3 that we have up here, can't we? Z sub r then is just going to be, right, r plus j0. Well, if that's just r, it's just out in this direction, so it's just going to be, you know, real. We know that. And its magnitude is going to be r, and ohms. And its angle is going to be 0 degrees because it's going to be directed R right out here. So something that's purely resistive is going to be in that direction, right? Out on the real axis, the x-axis, and at an angle of 0 rotated off the x-axis. Z sub L is just going to be omega L. That would be the magnitude, and then the angle is going to be 90 degrees, right? Do you see why I say 90? Because if I just had a pure reactance there, x sub L would only be going in the positive imaginary axis, right? In the positive imaginary axis. And what would be its magnitude? Its magnitude would be omega L, right? So, yeah, I shouldn't have put those two things there, but whatever. So that's what its magnitude is. And it would be in the positive 90 degrees, you know, the imaginary axis. And so that's why I've got, and I'm going to put a plus right in front of that just to emphasize that point. But then you see Z sub C. Now, a magnitude can't be negative, can it? So the magnitude is 1 over omega C, right? That's the magnitude that we have. Even though it's minus 1 over omega C, the minus 1 comes into account in the direction. So I could say that this is really minus 90 degrees. Now you say, oh, we can't use minus 90 degrees. Well, we're not taking any square roots or anything out of this. So really, as far as just, you know, we're being adding and subtracting phase differences, it's not really necessary to use the 270. You could use the 270 and it would work out just as well, right? So I could say that Z sub C is that, or I could say that Z sub C is 1 over omega C at an angle of plus 270, right? So, and that's the more correct way to do it. But believe me, what we're going to be doing in this course is it's not going to make a difference if you use the negative, which will be more advantageous in doing your calculations and everything else. So I just wanted to point that out. Now, what I said today was that we are going to do power. And so far, I've just been talking about impedances here. So let's just look at, oh God, that parentheses line is going to be over the line. I don't know. You'll have to just remember that it's there when I scan these in for you and send them to you. All right. Now, let's just look at a waveform, right? I'm just going to look at a sine wave. Right? And yes, that wasn't a very good sine wave that I drew there. It looks like the second lobe is much larger than the first, and it is, but hey, what can you do? It looks like a sine wave to me. Now, just a second. Okay, I'm back, I think. I don't know. But I'm going to go ahead anyway. I think that I am recording. Yeah, I had a phone call there, sorry. Whatever. So, we have this, and let's call this the voltage, right? So if I was to write a time domain form of that voltage equation, that voltage per time would be its magnitude. And we could say that its magnitude would be 10 volts, right? So if it's 10 volts times the sine, because it's a sine wave, times omega t. 10 volts sine omega t. And we can write that as a complex number notation too. So we could say that V equals 10 volts plus J0, because we're saying that this is the start. This is our reference voltage that we've got coming out. And we've got a small circuit like this. Let's say that the circuit is AC waveform going through a resistor. Now, what does the current do? We know that the current going through that resistor, and I'm going to say this is plus and this is minus and this is grounded, but in fact, we know that we've got a positive voltage right here, positive voltage, and here we've got a negative voltage. So the voltage is going to be changing all the time. It's going to be causing the current to flow in this direction once and then back once. And so it's going back and forth through the resistor. And as it goes back and forth through the resistor, it causes a dissipation of power, right? So we know that power equals VI. And we know Ohm's law, V equals IZ. So if V equals IZ, then I equals V over Z, right? So, and power equals V times I. That's what I'm getting back to. I'm always getting back to the power. So let's look at how the current would flow through that using Ohm's law. And hopefully I can get one of these that actually works. And now the current would be coming out like this, right? The current is going to be in phase with the, and there you go. I've got a pen that's a red pen too. Look at that. So you can see that the voltage and the current are in phase with one another. And how do I know that? Well, let's look at the current. Let's actually look at this. Now we know that this is the time domain waveform. And then we know that this would be the representation of the voltage because the voltage is starting right at 0. It's our reference. And we could also write that voltage as V equals 10 volts because that's the magnitude. And then what is the angle that would rotate? Well, let's look at this. 10 volts plus J0, just like R plus J0, right? So it would be at 0 degrees. So let's look at what the current would be. Current then is going to be voltage, which would be 10 volts at an angle of 0 degrees, divided by the resistance. And let's say that the resistance is 10 ohms, right? So if it was 10 ohms, then 10 ohms at an angle of 0 degrees too. Well, let's do that. 10 volts divided by 10 ohms, well, that's 1. So we know the current then is going to be 1. And what would it be? Volts divided by ohms, that gives us amps, doesn't it? And how do I know that? Well, I know that a volt is a kilogram meter squared over amp seconds cubed. And I know that a ohm, and since it's on bottom, I'm going to write it upside down, is a kilogram meter squared over seconds cubed amps squared. So you can see that everything cancels out, right? The meters squared, the kilograms cancel out, the seconds cubed cancels out, that amp cancels out with all but one of those amps. So I am left with amps. And now that was peak voltage, wasn't it? Right? That was peak voltage, and of course that's how we write it usually. And so now I've got 1 amp peak, and what is the angle? Well, 0 degrees minus 0 degrees gives us 0 degrees. So I've got 1 amp at 0 degrees. Now let's look at the power, right? Now, if you look at it, both the voltage is positive there and the current is positive there too, isn't it? And the current is negative down here and the voltage is negative down there. So positive times positive, right? V times I, positive times positive gives me a positive, and negative times negative gives me a positive too. So I've got two positives. And so when we look at the power, we can see that the power, positive times positive, is going to give me a positive power for the first half cycle. And then negative times negative gives me a positive, so that gives me a positive power for the second cycle. Now, what do we mean by positive power? We mean power is leaving the system. Power is being dissipated in the resistor as heat. Now, you don't, when we're working with our small circuits, we don't have enough current flowing through them to actually heat those resistors up enough for you to feel that they get hot. But if we ran a lot of current through those resistors, believe me, they would get hot. And that's the power that we're seeing. And of course, what is power then? Power is in watts. So let's just multiply this together. If we were looking at the power then, the power, again, we want to write these in phasor form, don't we? So because we're multiplying things together. So I've got 10 volts, but can we actually multiply 10 volts times the 1 amp and find out what our power is? Is that what we would do? No, because if you remember, these are all peak, right? These are peak powers here. Peak current, peak voltage, and we can't use peak voltage, can we? Because we know that when we're figuring out power, power is always V RMS times I RMS. And what is an RMS waveform as compared to a peak waveform? Well, we know that the VRMS is going to be equal to the peak, so 10 volts peak, divided by the square root of 2. And of course, the square root of 2, that's something that you should always know. The square root of 2 is going to be 1.414. And 1 over the square root of 2, which is what we're using there, isn't it, is going to, of course, be 1 over 1.414, or 0.7071. It actually continues on forever, just like 1.414 continues on forever, but of course, 0.7 rounds to 1. So that's what we've got here. So we've really got 7.071 VRMS, right? And when we look at IRMS, IRMS is going to be 1 amp peak divided by the square root of 2, or it's going to be 0.7071 amps RMS. So when we figure out what the power is going to be, we've got 7.071 volts RMS times 0.7071 amps RMS. All right. And of course, what you can see there is P is going to equal 5 watts. And you can see that because really we're multiplying the square root of 2 by the square root of 2, right? Because it's got square root of 2, so it's really 2. Square root of 2 times square root of 2 makes 2. And then on top, you've got the peak, right? The peak voltages, which are 10 and 1. So 10 times 1 divided by 2 gives me 5. And that's where the 5 watts comes in. And that, of course, is 5 watts that we're losing because we're heating up the resistor with it, right? I'm going to, I think, hold it right there. And I'm going to talk in the next video about how power translates in pure inductors and pure capacitors in an AC waveform. And I think it'll be very interesting. Who knows? All right, let's see if I can actually get this now to turn off. Oh, I think my thing is right there. He goes.